Good afternoon. Today is Thursday, March the 19th, and our lesson on the energy unit today is all about energy, which is a beautiful thing. All right, we're finally getting down to the meat and potatoes of what we're supposed to be talking about today in this unit. And so, just like work and power are words in the English language that have very specific meanings, but not necessarily physical meanings. Energy is actually very similar. We talk about energy reserves, and our country is energy independent, and all sorts of other things. But in physics, in classical Newtonian physics, energy is the ability for an object to do work. Okay. Now, I have done a great deal of work in collecting all of my possessions and bringing them back home to the bunker. You'll notice that I'm no longer in my classroom. It's day 3, so I figure it's time to go into hiding and that kind of thing. But in any event, energy is the ability to do work. All right, the ability to do work. And that'll pop up on your screen in just a minute. But think about this. We defined work the other day as taking a force and using it to push an object through a certain distance. And so if you've got energy, or if you're talking about energy, that really means that you've got the ability to apply a force to an object and make it move from one place to another. Whether you're talking about moving a refrigerator across your kitchen floor or even a spaceship through space. All right, moving that thing is going to require energy. Okay. Now, energy in and of itself is a scalar quantity. It does not have a direction associated with it. Okay, but it is the ability to do work. And because it's the ability to do work, it actually has the same units as work. Remember what those were? Do you? Do you really? All right, the units are, of course, joules. All right, now, the unit of joule, of course, is named after the famous scientist Joe Joule. And it turns out that because energy is the ability to do work, it has the same units. Okay, but we define energy, interestingly enough, mathematically with a formula that involves power and time, and that formula just popped up on your screen there. Energy is equal to power times the change in time. So it's the amount of power that you exert multiplied by the unit of time that you exert that power. Now, if you look at the units line again, you'll notice that it says a watt second is equal to a joule. Well, that makes sense if you think about it, because watts are a unit of power, and seconds, of course, are a unit of time. And so a watt second is a unit of energy, if energy is equal to power times time. And if that's the case, that energy and work are essentially equivalent, then the units of watt seconds, or joules, are the units not only of energy, but also of work. Now, this brings us to our example number 4. So let's spend a minute here and read through that. The question says, how much energy does a 60-watt light bulb use in 60 seconds? Again, we're going to do this problem the same way that we do all of our problems. We're going to build ourselves a laundry list, take out our handy-dandy reference tables, and look up the formula for energy, which we just saw in the previous screen. Energy equals power times time. Okay. Now, so how much energy does a 60-watt light bulb use in 60 seconds? So let's go through this, all right, shall we? For example number 4, the question is, how much energy? So the first thing that I'm going to put on my laundry list is energy. And energy, of course, is my big fat question mark in this question. That's what I'm looking for here in this problem. does a 60-watt light bulb. Um, and so in this case, the amount of power that I have is 60 watts. Notice how many sig figs there are in that number. And the unit for power, of course, is watts, abbreviated with a capital W. Um, so how much energy does a 60-watt light bulb use in 60 seconds? And so my delta T value is going to be 60 seconds. All right, notice again the number of significant figures that are in the time value here. So I get out my handy-dandy little New York State reference tables, and I look for the formula that deals with energy. And lo and behold, woo! I find it. It's energy equals power times the change in time. Now, there's no algebraic rearrangement required in this particular formula, and so all I have to do here is plug and chug. So energy in this case is going to be 60.0 watts times 60 seconds. And of course, as you can all figure out right now with your handy-dandy little magic number boxes, you can find that the value of the energy here is going to be 360 watt seconds. Okay? Or, of course, because a watt second is equivalent to a joule, we can write this as 360 joules. Notice that there are only two significant figures in the answer here because our value for time only had two significant figures. All right. Now, energy in and of itself comes in a variety of different forms, and we're going to talk about two of them today. All right. The two major forms, of course, are kinetic energy and potential energy. And these are things that you've probably talked about before. I know you talked about kinetic energy in terms of heat and in terms of the movement of molecules in chemistry. But for us, we're going to concentrate on objects that are on the middle of or in the middle of the scale. We're not going to talk about tiny little objects like electrons and atoms, and we're not going to talk about huge items like solar systems and even
it's 5 o'clock.
Well, thank you, Jesus. So the first energy, of course, is kinetic energy, the energy of motion. And so what does it take to figure out what the energy of motion actually is? Well, it depends. If you're moving a teeny-weeny object across a room, it's not going to take nearly as much energy as it does to move a very large object across the room. And so mass is going to be one of the things that's very important to know in order to calculate kinetic energy. The second item on this list, in this formula that you can see now, is the velocity. The faster the object moves, the more kinetic energy it has. And the one thing I do want to point out to you is that this is an exponential relationship. And so if you double the velocity, you actually quadruple the kinetic energy. If you triple the velocity, what do you do to the kinetic energy? Turns out that you multiply it by a factor of 9. So let's see how this might work itself out in an example problem here. In this example, I'm going to do a couple of different things, but let's read through it first. A 20 Newton block. Notice I didn't give you a mass here, I give you a weight, so we're going to have to convert weight to mass. A 20 Newton block falls freely from rest. So, initial velocity, 0. Acceleration of gravity, which is 9.81 meters per second squared, at a height of 3.0 meters from the Earth. What is its kinetic energy after it has fallen 1.5 meters? So I've given you a delta Y value. Okay. And so we're going to have to do a little bit of calculating. Excuse me, calculating. Just hit puberty 10 minutes ago. But we're going to have to do a little bit of calculating to figure out what the velocity is after this thing has fallen 1.5 meters. So how do we do this? Well, again, of course, we start with our laundry list. And because I'm trying to do this on a PowerPoint, I'm going to solve the problem in a slightly different way than I usually do. But again, always, we start with our laundry list here. Oh dear, I screwed this up. So I'm not going to go back and fix it now because I'm already recording and I don't want to leave the bunker. So the first thing I'm going to write down is that the force that we're applying here is going to be equal to the weight of this box. All right, and so it's going to equal 20 newtons. The initial velocity of this thing, because it fell freely from rest, is going to be 0 meters per second. And the height was not 50 meters. The delta y value is 1.5 meters. The height should be 3 meters. I'm not really sure why I have 50 in there. I did a lot of cutting and pasting in this, so that's probably it. But your height value that you see right here, this should say 3 meters. Sorry about that. In any event, the first thing I do here is I go through and I calculate the value of the mass. Well, if weight is equal to mass times gravity, then mass is equal to weight divided by gravity. Then I come up here to my velocity formula. Vf squared equals Vo squared plus 2a delta x. But because the initial velocity is 0, I'm going to change that formula to Vf squared equals 2g delta x. Notice I changed the value of the acceleration here to g because we're falling. It's an acceleration of gravity. The formula for kinetic energy is 0.5, 1/2, times mass times Vf squared. So since m, mass, is equal to W divided by g, and the final velocity squared is equal to 2a delta x, I'm just going to write the formula here as kinetic energy equals 0.5 times W divided by g times 2a delta x. Now I plug and chug my numbers in here. And you can do this on your own. Enter them into your magic number boxes, and you end up with 30 joules as the answer. Okay. That brings us to our next little trick, our second major form of energy, which is the gravitational potential energy, the energy due to the position. Okay? And because we are earthlings, or at least most of us are, yes, I'm talking to you, Dom, we refer to the gravity of the Earth here. So gravitational potential energy is the energy due to position above the Earth. The formula for this is, should pop up now, come on, there we go, is potential energy equals m times g, acceleration of gravity, times h, the height above the Earth. And again, this formula and the kinetic energy formula are both found on your handy-dandy reference tables. So let's look at example number 6 now. What is the gravitational potential energy of a 25.0 kilogram object suspended 38 meters above the Earth? All right, I'm going to go quickly because my video is running out of time. But for here, for example number 6, we're going to enter into we're going to do our laundry list. So here comes our laundry list. First things first, the gravitational potential energy. Notice I put that little subscript G there to tell me that it's gravitational potential energy. That's going to be our big fat question mark. We know that the mass of this thing, whatever it is 25.0 kilograms. And I know that the height above the Earth is going to be 38.0 meters. And of course, the acceleration of gravity is a constant at 9.81 meters per second squared. All right, I'm going to quickly plug that in. Potential energy is going to equal mgh, and therefore the potential energy is going to be 25 times 9.81 times 30, which is going to give me a grand total of 9,320 joules. Okay. Pay very careful attention. Your homework tonight is the energy homework questions 6 through 8, and there will be a quiz tomorrow on questions 1